Okay, so let's start. It is my pleasure to start this new 2023-2024 series of the AAAC seminar series. And it's even more a pleasure to introduce our first speaker, Joost Broekens, who has been, well, a friend for a long time, but it's very well known to this community for many reasons. One is he's been president of the association for quite a while. He's been very, very strongly involved in many activities, also making the link with the E3 conference, organizing special sessions. And many other things. But he's here today for his research, and he's also very well known for, I would say, maybe two main things that come to mind, others as well, but the two main things are his work on reinforcement learning and emotions, and I would think also of his modeling and taking into account and developing tools to include a dimension that is not so often taken into account in models. So besides valence and arousal, we have dominance. So he's done quite a bit of work on that. Okay, I'm going to quickly read the bio that's on the on the website. So Joost is associate professor and head of the Affective Computing and Human Robot Interaction Lab at the Leiden Institute for Advanced Computer Science, Leiden University. As I said, he's been president of the AAAC, and he's co-founder of the Interactive Robotics and of DAISYS. His research focuses on affective computing, in particular computational models of emotions in reinforcement learning and computational models of cognitive appraisal and human-robot interaction. So I think I will stop here, and Joost, the floor is yours.
Thank you very much, Lola. Thanks for the very, very nice introduction. Can everybody hear me, or everybody? Is the volume okay like this?
Yeah.
Yes.
Yeah. Yes. Okay. Cool. Yeah, it's the pleasure is entirely mine. I'm very happy to be here, and also very happy to be the first one continuing this magnificent series that Lola has been organizing so well in the last year. Yes, I thought it was fitting to talk about my pet topic. Let me put it that way. So it's indeed something that I've been looking at for quite some time, together with students, but also other colleagues, and it is the idea that you can actually computationally simulate or understand emotions by computational simulation of what's called the temporal difference assessment in RL. And I'll explain what that is, and I will show today a bit of an overview of the work, computational work that we've been doing to try to find out if this actually makes sense. And I'm not going to cover too much of the psychology and neuroscience here. There are many people, of course, also in neuroscience that have been working on trying to find out, for example, brain regions that both are involved in emotion processing as well as in RL-related assessments. I'm not going to cover that too much here. I want to focus a little bit on the simulation. But first, some intuition. For some reason, yes. So, just this is a video. I hope I'm gonna. Yeah, let's put the sound down. So what you see here is a rat, and this is just a random. Well, it's not random. I chose it for a particular purpose, of course, but it's a video of a rat playing, multiple rats. They're playing. They're showing affectionate behavior. They show play behavior. Play as in trying to explore, figure out how things work. and they are obviously enjoying it as well, right? So I think this is an important, yeah, I would say intuition for the fact that playing, exploring, interaction as well, social reward, that all of these things, they are very important for animals, at least these types of animals, to develop. And I'm gonna cut it short here. I think this is a particular thing that is important for many animals that are raised by parents. And I put it that way on purpose because I don't want to exclude, for example, animals like birds who are also raised by parents. Huh? So there seems to be this relation between playing, between exploring, but also emotion expression, and the fact that these things are usually activities that there seems to be some motivation for, some intrinsic motivation. And I think an important element here is that all of this can't be done without the safety of a sandbox provided by your parents, right? So in a way, all animals that are, let's call it, born underdeveloped in terms of their behavioral repertoire, they need some form of supervision and safety and some form of freedom. And it is in this particular environment that by the sort of intrinsic motivations that we were given evolutionary wise, these animals can develop a quite broad and also quite diverse set of behaviors that would otherwise be impossible given of course, the amount of development that they have, the amount of time and effort that they can spend in development. Let alone, if you would do this without supervision, you would probably simply die. Because you're starting to do very stupid stuff, and at some point that is definitely not evolutionary beneficial. And we can see that feedback signals play an important role in this shaping. And I'm not arguing that feedback signal is the only way we learn, of course, but feedback signals are important for shaping, not only feedback signals that are internal, feedback signals that come from, let's say, hormonal or hormone-based reward systems, or from hunger, thirst, etc., but also social feedback signals from your parents or your peers. And in a way, this drills down to what you could say rewards and task learning. And I don't say by this that everything that we do is reward-based task learning, but it is an important mechanism by which we can develop a diverse set of behaviors. Again, rewards may come from many different sources, right? So this is, if we look at the arrow, this is like a top-down view from emotion and play to reward and task learning. But what I want to do today is computationally show how you can also sort of reverse that process and say, oh, let's start at reward and task learning and figure out if there is a way and to what extent can we use that as a model, a formal framework to understand what emotions are. So the overarching research question I think I've been looking at in the last couple of years are, how did emotions evolve, and why do they seem to exist in so many species? How do emotions develop related to the cognitive and behavioral complexity of an individual? For example, children, very young children, they definitely have, of course, emotional experiences or affective states. And I mean, that's true. But the, let's say, complexity of the affective states that they can experience probably depends a lot on the cognitive complexity and the behavioral complexity that they can actually show and cope with. The emotions such as guilt for doing something to someone else, knowing that you had an alternative. These are, of course, emotions that we are very, let's say, accustomed to, but very, very young children probably don't experience guilt in that particular way when they're 1 year old. And that's probably, there's probably a reason for that. So the question is why? And what is the function of emotion? If you may speak of a function of emotion, and I think from a philosophical point of view, when we're done with this talk, I think the question, we should probably revise it maybe for the Q&A. Is there, if you look at it at the way I look at it now, does emotion have a function, or is emotion another word for something that simply happens all the time? How do events elicit emotions? Okay, and from our applied perspective, of course, and you can, and my applied perspective is robots and socially interactive agents, of course. Can they be grounded in a machine learning process? And what would that mean? And is that something that is useful on top of, or maybe an extension to computational modeling of appraisal theory? So in a way, can we ground this in the learning process itself? And then another aspect is, can these emotions help the interaction between humans and agents, and especially by making use of them to sort of enhance the transparency, or to reduce the ambiguity in what you see in the behavior. If you look at a robot or at another agent, human agent, if you look at them and they're doing something, sometimes it's difficult to infer the intent of that particular behavior, and emotions might be a way for us to better understand why someone is actually doing something. And we could perhaps use that also in adaptive robots in a way that help us better understand what's happening in the robot. Okay, so the proposal is really about emotions and formalizing them as sort of a part of the reinforcement learning process. But first, reinforcement learning real quick for those who are not too familiar with it. So a way I like to say is that it's of course a computational model for learning goal-oriented tasks by exploration and delayed reward. But it's essentially a way of saying this is instrumental conditioning plus plus, and the plus plus really refers to the fact that this signal, this reward signal or punishment, but let's abstract away, let's say reward signal, it is also a signal that can come in several steps later, so it can be delayed. And reinforcement learning is a sort of a formal framework that allows you to propagate back and do credit assignment of that reward over time, integrating to something that's called, let's say, a value. And the value is supposed to be an expectation of sort of the good and the bad stuff that you anticipate in the future based on your experience. And many of the processes in reinforcement learning seem also to be happening in animals, including humans. Now, the key idea is, while you're exploring, you experience both changes in your environment, but you also experience rewards. And the key method for updating the anticipation of how good or bad something is what is called the temporal difference error. And it's a learning signal, essentially. It's telling the individual how to adjust the value of the last action that you did based on the recently received reward and your anticipated future reward. It's like saying, okay, I learned this new thing, now I get a nice reward. That's more than I used to expect. So let's change my expectation for the future, for the next time I'm here, essentially. And that change, that difference, that's the TDRL. Now, mathematically, and it's the only slide with a function on it. Well, there might be some later, I don't know. Who knows? This is just a standard reinforcement learning, model-free reinforcement learning method called SARSA. It's already very old, doesn't really matter, but it's the easiest way to show what the temporal difference is. It is the element behind brackets, and you can see it's essentially the update. So the old value, so that's, excuse me, the new value is on the left side here, the QSTAT, that's the value of a particular state, action, becomes the old value plus an alpha, which is a change. It's like a weight times the change signal, and that's the temporal difference. And essentially, it's the reward you get plus some discounted future value minus the current value again. So that's essentially saying it is the difference in your expectation. And now I'm going to update my current estimation of how good I'm doing according to that estimate. Right. Now, this incorporates two things, namely the reward, RT, which is the reward at the current moment, the current transition, which could be a block or block of cheese, excuse me. But it also incorporates the future, because that is essentially the QST plus 1, AT plus 1. So that's like the accumulation of rewards in the future. So what's important to remind here that the temporal difference signal is not just based on the reward. It is not the reward signal, right? But it's like a derivative of the reward plus anticipation of future stuff. Yeah, that's essentially a way to look at it. So it's more than just the reward. It's really the change that you need to do, positive or negative. All right. So what I propose is actually a very simple hypothesis for emotion. So what I'm just saying is emotions are the manifestation of neural temporal difference assessment. So that simply means whenever you do or an animal does a neural temporal difference assessment, they experience at that point also an emotion. And I'm not saying that that's a simple assessment. I'm also not saying that the reward is a very simple signal, right? I mean, of course, you need a in nature, a very sophisticated body with a lot of homeostasis and a lot of hormonal systems to be functioning for you to be able to actually do something like that, right? So it's not saying this is easy. I'm just saying that the neural temporal difference assessment is something very specific. Namely, it is a signal that you get when you change your view of how well you are doing. And the funny thing is, in my view, is that this signal actually arises in a situation that very much matches what we normally talk about when we say emotion. It's event related. It is something related to a particular current happening. It's valenced. It's positive or negative to some degree. It's relatively short-lived. Because you experience it now, but the update it wears off after a couple of interactions, and then you're ready for a new one. The intensity is very much related to the relevance of the event, the way you see it, and it's also very much tied to action tendencies, because what the temporal difference assessment in the end is sort of responsible for is that your tendency to do actions in that particular direction will be automatically updated as well. So temporal difference assessment is almost the same as an action tendency change, essentially. And that's funny because those are essentially things that we've been saying, oh, these are elements of what an emotion is. Okay, so, and I'm proposing, for the sake of simplicity of today, that are at least 4 emotions that you can relatively easily define based on this idea. There's distress, which is the actual negative adjustment. So that's a negative temporal difference assessment. There's joy, that would be the actual positive adjustment if something happens that makes you update how well you think you're doing. Then there's fear and there's hope. And fear and hope are anticipations of negative adjustment, of positive adjustment. I'm going to explain what I mean in detail. Yeah, so this was the remark that I made. I'm not saying that this is simple. I'm not saying that emotion is just reward and punishment. I'm not saying it's not social, because social processes can result into experienced rewards. So there's a lot of what it is not, but it is a very simple hypothesis. Let me put it that way. Maybe too simple, but who knows? Okay, so as an example, so temporal difference reinforcement learning, emotion of joy. If you transition from now to a next state and you experience a temporal difference that's bigger than 0, you would experience joy. If you would experience one that's negative, you would experience distress. And I'm calling it distress. I'm not calling it sadness. Sadness is something, I think, way too specific to call an emotion like this sadness. But distress is probably the sort of the right undifferentiated way of calling it. There are model-based temporal difference emotions that have to do with anticipation. So hope, for example. Now, hope is if I'm in the now and I'm trying to simulate or imagine, we humans call it imagination, or rumination if it's bad, but we imagine a possible future. And somewhere along that trace of imagination, we realize, ooh, but I'm going to win the lottery. Then that is a form of joy, but it's a specific form of joy. And we all know that it feels different. It's the form of joy that says, there might be something cool coming up. Let's go there, which is sort of a positive anticipation, right? Which is, and again, hope is a label, yeah. But that's the type of emotion that you would experience when you go that way. Hope. Okay, same for the negative side, fear, or I would call this anxiety or worry, fear, not the startle or the I'm sticking my head in the sand type of fear, but the worrying anxiety form of fear, sort of the counterpart of what you could call positive anticipation and hope. So you're in the now, you again start to imagine or ruminate, and then, oh, there's something potentially bad happening. Yeah, it could happen. That's not very nice. So you would experience this stress, or you're anticipating this stress. And because it's the anticipation of this stress, it feels like anxiety. So it's a different form of distress, essentially. Okay. So the outline of the argument really is as such. So if an emotion is a situational judgment of positive, negative, and it's involved in modifying future action selection aimed at survival of the individual, which is sort of an abstraction of what many emotion psychologists also feel is related to what an emotion is. And the temporal difference error is a situational adjustment of action value influencing future action selection aimed at optimizing long-term reward. Then essentially what we're saying is, well, and I colored the different concepts, but it's saying similar things, right? You could also say that an emotion is the manifestation of this situational adjustment simply, and it influences future action selection. And it's, of course, also optimizing long-term reward, whatever long-term reward means for me. Okay, so again, let's not get into the discussion of how many rewards there are for certain people or animals. I don't think that's I can't answer that question either, but at least there's something that I'm trying to optimize, and it better be good for me, and of course other people around me. Okay, so this is the outline of the argument. I'm going to try to show a little bit of the evidence as mentioned from computational studies. So I'm going to highlight a couple of different studies that we did. So there's a simulation of joy and distress. There's a simulation of hope and fear. There's the expression of this fear signal in a human agent, simulated agent interaction setting. Then we recently did a study, HRI study, where we simulated emotions using the same method and tried to find out if there was sort of a measurable impact on how people interact with this learning robot. And then there's a small study that we did for simulating regret. So if I have time, we'll get there, and if not, then we'll end, or we can ask questions about other emotions that might be possible. Okay, so first study I'm not gonna address. I'm gonna go to the fear and hope simulation immediately. Essentially, the joy and distress simulation study showed that joy and distress show similar intensity behaviors as you would expect from emotion theory. So they would, for example, habituate over time, or when behavior starts to becoming a habit, the intensity of the emotions go down as well, right? So this is like the typical type of correlation between habit forming and emotional intensity that you would see. Okay, fear and hope simulation. So we simulated fear and hope, and we simulated as, of course, anticipation of negative and positive adjustments. So what we did was, and it's important here, that's why I bolded the statement. So it's not the startle fear that we're looking at. We are looking at the anxiety type of fear. So the anticipation of a threat or danger a little bit further ahead that you have to essentially sort of cognitively simulate, if you wish. So that's why we use model-based RL to do this. Okay, so just to give you an idea of the sort of the reasoning behind this, and also the reason why you would need model-based reinforcement learning, or at least models that allow you to forwardly simulate, anticipate. So if you look at the left picture, you can see my son, and he is climbing on some pretty steep, doesn't look that steep, but it was very steep actually. But he's having fun, and he's enjoying himself. On the right hand, you see my wife with that same son on a different day though, but also a very different setting and a very different emotion also. So she is actually, and I was the same, but I made the picture so you can't see it, but she was actually quite anxious at this point. Now, why would she be anxious in that setting, even though the left setting is arguably more dangerous. In the left setting, my son does not experience anything in terms of fear, but my wife in the right setting is experiencing quite a lot of fear, and so was I. Now, I argue that is because my son in the left is not anticipating any negative adjustments. He's just in the now, playing, experiencing new things that he can do, right? So he's mostly experiencing positive adjustments in the now. So he's actually experiencing joy while he's playing and developing behavior. The right-hand side, my wife is not developing any behavior. She's actually anticipating what might happen. And even though there's an extremely small chance that he will just magically flip over the edge there, which of course won't happen because it's high enough for him not to fall over. It was high enough for us. There's still this very small possibility that it might happen, and that is a very bad consequence. So in her mind, she's simulating a negative adjustment, and it's this anticipation of negative adjustment that makes the emotional situation completely different in the left and the right setting. So we wanted to simulate fear in this particular sense. So we had an agent, S on the left, and we had a goal, a G on the right, and the agent has to learn a very simple policy, namely go from S to G. And the only thing is there is a shortest path to learn. It's reinforcement learning, so it has to repeat this a couple of times. But it's a slippery edge, so the agent can actually fall in. So it's not the most optimal action to just go right along this cliff. But this is the task it has to learn. Okay, so the policy is learn to go to the goal in a way that optimizes reward, i.e. get to the goal safely. It's essentially what we ask. And we simulated fear as this is a mouthful, but minimal temporal difference in anticipated sampled future traces in model-based RL. So essentially what we did is we had model-based RL, so we allowed the agent to learn a model of the interactions of the world, and then we allowed it to internally simulate future possibilities, possible traces, right? And the signal of fear for this agent is the worst possible future outcome somewhere, worst being the lowest temporal difference experienced somewhere along these lines, weighted by how probable it is that it will happen. This is essentially fear. And I'm not going to go into detail of these graphs, but the interesting thing is that if we manipulate the perception of control of the agent, perception of control meaning the amount of control it thinks it has while sampling future traces, or if we manipulate the closeness of the threat, so threats that are closer versus further away, or if we manipulate the amount the agent can ruminate, so the amount of sort of traces it can sample in its model, then those things actually modulate fear intensity in the way predicted. So closer threats result in higher perceived fear, more rumination in the with risk of danger also accumulates to a higher level of fear intensity, and lower perception of control also gives you higher perception of fear, which is essentially what is often seen as well in humans. Okay, so that was fear simulation. Now, the next step for us, of course, was, well, what if we simulate this fear and then show it to a user? So that's what we try to do here. We wanted to figure out what way of simulating fear, what rumination, what internal simulation of possible futures, what anticipation process actually results in a plausible fear signal. So we wanted to play around with the idea that fear is modulated by rumination and tolerance to uncertainty, essentially. So we needed to figure out a way to simulate sort of different ways of internal simulation, and that's essentially what we did. So we had an agent, and it had to solve a task. I'm going to tell you what the task is later. It had to solve a task, and it would do that. It would solve that task, and then we would simulate the amount of fear it would feel based on different thought processes, essentially, different ways of anticipating the future. Let's say analogous to someone who is very much imagining all possible random outcomes to be equally true versus someone who only simulates what it thinks is the most probable outcome of a scenario. So let's say someone who's thinking broad or someone who's thinking very narrow. Okay, and we wanted to know what is the influence of this rumination in computo to find out what it does to fear as shown to a human observer of that agent. Okay, so what we did was the following. We had an agent, and the agent you can see it in the top right. So there's this agent, and it's supposed to learn to get to a target. Again, these are always very simple tasks. And then somewhere in the middle, there's this really dangerous ghost. And it's a stochastic ghost. So it can pop up anywhere. It moves, but you don't see it. Ghosts, they're very difficult to see ghosts typically. So also for this agent. So there's a risk that you might stumble upon the ghost, but you don't know it, right? So this is the stochastic fear element that's of course needed. Otherwise, it would simply learn a habit, and in a completely learned habit, there are no temporal differences because you converge. So there's no emotion in the habit. So for fear to make sense, you need some uncertainty. And this is the type of uncertainty that we introduced. Now, that was not a manipulation. What we manipulated was the anticipation methods. And overall, we don't have to go through detail, but overall, these methods played around with how strict they would stick to what the agent thought it would do, so its policy, and how broad it would do it, how broad it would consider its possibilities. And it would also manipulate how far away the agent could actually look into its model in order to simulate the temporal differences that it might be experiencing. So it's like rumination far ahead or close versus broad versus narrow. Now, and then what we did is we plotted the perceived fear by the agent on sort of a heat map. And then we showed these heat maps to people. And then we asked in a MTurk study, okay, so which of these heat maps do you think best matches with what you would think is a plausible fear signal? Okay, we asked other questions, but for the sake of time, let's stick to that question only. So focus only on the right side of this slide. So that's the heat map, and that is the bar plot here. And what was very clear is that there is only one way of simulating fear that actually sort of stands the test if you compare it with either a completely random fear simulation baseline and all of the other simulation baselines. And that was quite surprising. So there's only one method out of the 7 that gave plots of where people thought it would be most plausible to feel fear, that actually made sense. And that was an epsilon greedy with a long horizon. So it means it is something that has some randomness in the behavior of the agent, but it mostly sticks to what the agent thinks it's going to do. But it's looking quite far ahead. So it is able to actually see relatively far into the future and then simulate what the fear is going to be. So this is again fear as in worrying/anxiety. Now, I'm not gonna claim anything about whether people are doing it in this way. What I'm going to say is apparently you can change the internal simulation strategy of agents and you get very clear differences in the simulated emotion patterns, in this case, fear. And that's an interesting way of sort of manipulating what kind of emotions you could experience in particular settings. So you have complete control over the way these agents simulate in their heads. And that's an interesting idea, right? Because if you can make those ways more biologically plausible than we did in this study, because this was just us figuring out 7 ways. But I mean, if you could actually think of ways that are more biologically or psychologically plausible, then you can implement those different ways, simulate them, and simply look at what the fear intensity is and how people think that that should be rated in terms of plausibility. So it allows you to simulate emotions very precise way, in a very controlled way, and you can actually detect signals from this type of simulation. Okay. Now, then what we wanted to do, and that's a recent work, is we wanted to figure out what if we simulate joy, distress, hope, and fear, and we do this in a simulation study. So on the right, you see a picture. There's one of the subjects. That's the guy. He's in front of the NAO, and there's Floortje. She's the student who did this very nice work, and she's sort of observing what's happening, wizarding, of course, sometimes a little bit, but mostly it was autonomous. But essentially, the subjects had to teach the robot a particular task, and the robot would either express emotions or it wouldn't, etc., etc. Okay, and the question was, what is the impact on the learning process and outcome of the robot and the human teacher's perception of the robot if simulated emotions are expressed by the robot when it's grounded in the learning state? Essentially, we simulated these emotions, joy, distress, hope, fear. We expressed them on the robot in one condition. We didn't express them on the other condition. And we had a third condition where the robot would express it, but also tell to what the emotion was coming from, to what it was attributed. And then we wanted to figure out, does it matter in the learning process, essentially? And of course, we thought it mattered, right? So let me put that up front. So robot expression, we had 4 validated expressions up front. Then we had a task, and the task was quite easy. Simply instruct a robot to show the correct color on its eyes. So it's a quite easy task. It was an actual MDP, so it wasn't just a slot machine, since for those with the RL background, it was an actual MDP, but very simple one. We used SARSA. We had 61 adults doing this study, and this was essentially the setup of the study. So people would just try to teach the robot what red is, and what blue is, and what green is. That's what it was. And the robot would get a reward. If it was good, the person would say, yeah, nice. And then we simulated the reward, so the people couldn't make a mistake. And then the robot would sort of learn over a couple of trials by reinforcement learning what the correct colors were. Okay, so as I said, we had 3 conditions: a baseline with no emotional expression, but some expression. Of course, it wasn't a static robot. That's not a good control condition. There was an emotion expression based on temporal difference, and there was emotion attribution. So that means that it, on top of the expression of the emotion, it would also say what it hoped and what it feared, sort of as an additional part of the information. Then we figured, okay, look at the learning progress. So how fast does it learn? Look at the learning process. Is there an impact on, let's say, exploration, exploitation? Do humans change things? Does the perception of the robot change, robot perception? And unfortunately, there was almost no impact. But the point is, that's of course possible, and we have to report this as well. So the only sort of statistically significant impact that there was, we also know why, we believe, but the only possible impact that there was that people luckily thought that emotions on robots were somewhat novel, so that's good, and they thought they were a little bit more animate. Which is essentially saying, well, the manipulation worked, and people also reported that they understood the emotions, etc. So there wasn't really something wrong with the setup, except one major issue, and we believe that this was the actual task. So the problem is that the task was not suitable in the end, and we put a lot of effort in making this task clear, simple, etc., etc., etc. And in the end, we believe that there are three key elements that missed. So it didn't involve sufficient robot autonomy, right? You have to imagine if you're tasked as a subject with the following thing: teach a robot colors, yeah, then essentially it doesn't really matter what the robot is gonna do. You're just gonna try to do that. Okay, so there is within subject variability at that point. Everybody will do something a little bit different. But does it really matter if the robot expresses something? If the very clear goal-oriented task for you as a human is teach it? Probably not. So it's not very autonomous. It could do it autonomously, but we didn't do that in the setup. So there was no intervention essentially needed. You're just driving the whole process. And it wasn't complex enough. So one of the basic ideas, and I have to say this is a stupid oversight of me, essentially, but it's, if the basic reason for wanting to do this is to increase transparency and to decrease sort of ambiguity, then there should be some ambiguity to resolve. And this task is so very easy, apparently, for subjects to understand. We didn't know that up front, right? We thought, people don't understand RL, they don't understand anything. But essentially, they really understand very well what was happening, because it was simply easy to sort of mentalize and keep everything in their head. So the task was not complex enough. It's too easy to oversee the progress. And a last thing, it doesn't really afford changing the learning strategy from the human, right? So why would you change your commands if the robot is fearful? I mean, what do? Decide not to teach it a color? So in a way, this is in retrospect, it's easy to say, yeah, it was stupid, but it did teach us that these are three very important elements that you need to take into account if you wanna study, let's say, signals that enhance transparency or explainability. You need to be able to measure it essentially in your task. Okay. I think for the sake of time, I will go to the final overall conclusions, Lola. Is that okay? Regret was just a study where we simulated regret also with the temporal difference RL model. I can answer a question about that later. It was a nice study though, but let's click through it. Tick, tick, tick.
Maybe you can have a few minutes actually for regret, because it's not, something
If someone, yeah, we
not
can.
very well studied. Yeah.
Okay, I can do that. Yeah, that's fine. Okay, so that's the end, by the way. So after that, I'm done anyway. So temporal difference model for the emotion of regret. So up until now, we've looked at four relatively simple to formalize emotions: joy and distress, which is the temporal difference itself, and then hope and fear, which is the anticipation in some forward model of a temporal difference error. Regret is sort of the extension of this to a cognitive process that actually does counterfactual thinking, essentially, in retrospect. So what is regret? So let's say conceptually, theoretically, regret is a devaluation of an outcome. That's the basic thing of regret. You regret something if something happens to you, and then you have to devalue what happened. But that's not enough, right? That's essentially what I would say distress. So whenever there's a devaluation of an outcome, that's essentially distress. Now, the key thing is that regret involves counterfactual thinking and an evaluation of an action history, knowing that there was another course of action that would have resulted in a better outcome. So you typically don't regret something if there was no alternative process that had a better outcome. Because then it's just, I mean, you can be sad, but regret is not the type of emotion that you would have. At least it's not a very healthy one in those sittings. But regret is emerging if you realize something is a little bit worse than you expected it to be, knowing that somewhere in the history, along the trace of stuff you did, there was a split point, a decision that could have ended you at a higher value than you are now. And by value, again, I mean, biological value is fine, social value, I don't mind. You assess this thing as better than the thing you end up here now. So you need to devalue your outcome, and because of the devaluation, something else became better. Okay. And there are feelings of sadness, despair, anger at oneself, all very plausible feelings and emotions. Essentially, if you look at it, that this is a very specific temporal difference signal. Anyway, let's go into that later. So what we wanted to do is, again, simulate different ways of thinking. So different forms of counterfactual thinking in an agent that had a model-based reinforcement learning approach, and where we could simulate temporal difference errors. So counterfactual thinking were variations of sort of revisiting the decisions made. And just graphically, this is again an agent. It's starting at the start position, and it has to learn to go to a goal task T. And at some point when it had learned this habit, we devalue T. So we just say, you just learned to do this, but now suddenly, now that you know or think to know this is good, we devalue it. And then, of course, the agent experiences a temporal difference at that moment, right? Because it changes the actual value of the last action, because suddenly it becomes worse. And then by doing that, we knew that C, which is the alternative outcome, would be slightly higher than the new T. Okay, so we devalue T after it has learned a habit, and then C becomes a better option. It doesn't know that C is the better option at that point. It has to sort of counterfactually think, right? So it has to figure this out at that point. And that's when we trigger essentially the thought process. So it experiences a temporal difference, and then we say, now think where that came from. Okay. Good. Now, what they did is, we simple Q learning, learned to fully solve the task, and then we devaluated the target, and then we simulated sort of the counterfactual thought process in 3 ways. We used backward SARSA and backward Q. Not going to go too much in detail in that, but it simply means update the values from the target back to the start position in a row, essentially. So you're just going to do cumulative updates, taking one step back every time. And that's a simple way you could think, let's go back what happened, update everything, and then check what do I regret most. The other one is a forward process, that is Monte Carlo rollouts, simply sort of random rollouts of possible futures, but from the start position. And then we just roll them out, and every time you roll it out, you also do what they call a backup. So it's like forward simulating a lot, updating your model while you're simulating possible futures. Forget about the regret intensity. It's just a computational model of what I just explained 2 slides before. Now, the funny thing is we had interesting results. So in the case for SARSA and for Q updates, the regret signal in intensity plots for regret wasn't very plausible. So the SARSA updates along the trace, and this is of course computationally not surprising, it gives the most regret to the last done action, because that's essentially where the biggest TD is happening. For Q updates is even worse. I'm not going to explain why, but that's simply because the way Q updates work. So that's like the middle picture. But for the Monte Carlo updates, we get exactly the most intense regret at the moment where the actual choice has or was. If the agent would have had to sort of revisit what it was doing. And that's the interesting part. So it seems that Sarsa and Q updates are not really counterfactual thinking processes, but Monte Carlo updates actually have that characteristic. So they simulate possible futures, and while simulating possible futures, you try to figure out what the impact is, and then you update the value. And it ends up exactly at the split point, showing that this really is a sort of a model-based approach. So when you regret something, you actually, according to this computational study, you actually try out alternative futures from some imagined starting point and then decide, oh no, I should have done that. Now I regret it, right? So it's like a forwardly simulated counterfactual thought process. It's not the temporal difference itself. That's the sadness, that's the distress. But the regret really comes from this process of simulating possible sort of alternatives in this study. Okay, so that was regret. Overall conclusions. I think that computationally, if you look at it, seems that at least learning and reward processing are coupled to emotions and affect. At least you can formalize them in that way. There are, of course, other ways of formalizing emotions in reinforcement learning, right? I don't want to go into that too much now, but you could also appraise or do, for example, cognitive appraisal and try to formalize appraisal processes directly in a MDP type of formalism. But I'm focusing on this temporal difference assessment here. And then, well, the study about the transparency is not conclusive. Now we think we know why that was, because the task wasn't suitable. So we're going to work at that together with Bernard Hilbert, a PhD, who started here last year. We're going to try to find out ways to sort of experimentally do this in a more structured way. Yeah. So that's it. Thank you very much.
Thank you, Joost. Top on behalf of everyone, and I can say that I definitely do not regret inviting you. Thanks for this talk.
Yeah, that's a nice joke. Yeah.
I'm going to stop the recording now, and if people have questions, maybe you can use the hand, raise your hand, or just open the microphone and ask a question. So I stop now.